The 250 megawatt physics teacher. Tesla is now burning 250 megawatts of power at Giga Texas to solve the most boring problem in robotics, the physics of friction. While early Optimus iterations relied on hard-coded heuristics and teleoperation data, Gen 3 is the first to run on a massive video generative world model trained exclusively on the Cortex supercomputer. This shift from manual scripts to learned physics starts with how Cortex processes millions of hours of fleet data to understand mass and momentum. Scaling the physics bottleneck. To move a robot through a messy factory, you cannot just show it what to do. You have to teach it what happens next if it fails. Tesla is using Cortex to run massively parallel simulations that bridge the sim to real gap, using a technique called generative physical prediction. Think of it like a video model that predicts the next 10 seconds of physical interaction before the robot moves its actuators. If the prediction matches reality, the weight of the neural network updates. Critics point out that video prediction is not the same as causal understanding, and we have yet to see Gen 3 handle high-variance lighting or non-Newtonian materials without significant jitter. But the raw compute required for these billion-parameter predictions is precisely why that 250 megawatt requirement exists. The high-dimension data problem. Training a robot to understand three-dimensional space from two-dimensional video tokens is computationally expensive. Cortex is not just a collection of accelerators. It is an integrated thermal and power environment designed to keep clusters at peak utilization for months on end. While a large language model might need 50 billion tokens of text, a world model for robotics requires petabytes of high-resolution video frames at 60 frames per second. This is a higher dimension of data that requires the low-latency interconnects found in the Cortex architecture. Tesla's move to this scale suggests they are betting that compute scaling laws for robotics will mirror what we saw with language models, where sheer volume eventually overcomes edge case failures. The foundation model for physics. The real takeaway from the Cortex build-out is that Tesla is no longer building a robot, but a general-purpose foundation model for physics. By moving past the prototype phase, Gen 3 demonstrates that the primary challenge has shifted from mechanical design to a data scaling problem. For developers and engineers, this means the competitive advantage is now the ability to simulate and verify physical interactions at a planetary scale rather than fine-tuning a specific grip or gate. If Cortex successfully reduces the fine-tuning time for new factory tasks from weeks to hours, the bottleneck for deployment moves from the laboratory to the assembly line. The metric to watch over the next 6 months is the mean time between interventions in unstructured environments, which will prove if this compute wall actually translates to physical reliability. Watch for the first deployment of Gen 3 in non-Tesla facilities as the true signal of maturity. Subscribe for more.